Okay, so in this video, I'm gonna show you a little bit in details what the balance variances means when we evaluate our model fitting. Okay, uh, so usually you have the underfitting. Underfitting means too much biases. So for example, in our previous data, the underfitting, our model, our ground truth is this pretty nonlinear sine curve with linear trend. But if we only use a line to fit it, we ignore this seasonal fluctuation. So, which means our model is too simplified. So we only use a simple linear regression to fit this nonlinear term. There's a bias there. So which means our model is too simple. So which means we have very big bias between the ground truth and the hypothesis model H. That's called too much bias. We get more overfitting. And so that's first one. Second, most overfitting caused by too much variance. Most overfitting caused by too much variance. Okay, overfitting means you have some data point. You suppose you observe some data point here. Here we only have the sine curve, but if you have the polynomial with power 10, so you might have a model that goes through every data point. But when you change another data set from the ground truth, simulated from the ground truth, your model will perform bad. This is called overfitting. Too much variances, model variance, too much model variance. So in other words, when we simulate another data, our model is totally different with the previous one. Okay. Third observation we have is training error reflects the bias. But not much variance. Because when you talk about the variance, model variance, you need a new data set simulated from ground truth. You can get the variance. So training error, even though you have the training error, that only reflects the bias of your model. So your model works very good on the training data set. Don't be too optimistic. There might be a big variance there. And the test error can reflect both. Test error means you once you train your model, you want to apply your model to some new data set, which you do not know the answer when you train the data. Okay. And number 4 observation is usually for many distributions and models and the distributions, as the sample size increase, okay, the variances will decrease, goes to 0. Okay. Number 5. If H can fit G exactly, so in other words, if you accidentally pick the correct formulas, which is same as that contains the true ground truth function, if this hypothesis model cannot fit G well, can fit well, sorry. So there are two scenarios. Suppose this ground truth G this H, your hypothesis function, happen to contain the true function. Okay, for example, you apply the polynomial regression function with power 2, degree 2, and the ground truth is happen to be a parabola function. Okay, then the Bayes will go 0. If your sample size goes infinity, the Bayes will go 0 for many distributions in general. Okay, 6. So that's a perfect case, right? That's a good case. But most of the real applications, we do not know this unknown ground truth. We just guess a function, right? Hypothesis. So if H cannot fit G well, Bayes is large at most points. Most points. Okay, 7. Adding features will reduce the biases. For example, original model is y equal to a plus bx. So now you add more features. You transform, for example, the cx squared plus dx cubed. You keep adding the features. Add a feature in general reduce the biases. Model bias. Because you can have more flexibilities. Adding bad feature rarely increase it. And number 8. But adding feature usually increase the variance. So you do not want to add features that is you want to add some complexity to your model, but you do not want to include too many features, too complex models. Number 9, irreducible error cannot be reduced. You cannot reduce irreducible error. Noise in the test set only affects variance of E. Noise in test set affects only the variance of the epsilon. Okay, so in the third term, this part. But in the training error, okay, noise in the training set affects both spares and variance. Spares of H and variance of H. So here is just some good example that suppose our true function. This is a picture from our textbook. Okay, the ground truth is this black line. Truth is this nonlinear, show some nonlinear curve. And the data set is fit with splines has various degree freedom, so which means more features. The synthetic data is taken. The black curve is with added noise. At the center, we plot the training error. So this is the training error. So we have the black line. This is the training error. Okay, and the test error. This is test error. So as we can see, the first model we try is just a linear model. So obviously it's underfitting, right? So at the beginning, both the training error is big, also the testing error is also big. And after we increase the model complexity, we add in more features, our model fits better and better. And we can see here at some data point, our function with relative more features has this blue curve. Blue curve has small training error. Okay. And if we keep adding more features, okay, we get this really really curly curved model with up to 6 degrees with more degrees. Okay, as we can see, the training error keep decreasing because it's trying to fit every data point in the data. But is that a good sign? No. As we can see here, for real application, when we apply this model, this really curved complex model to the new data, the testing error will start to increase at this time at this point, which means you start to be overfitting. So start to overfitting. So below, on this side is underfitting. Okay. And on the right hand side, we plot the square error loss as the sum of the squared bears. So this is the bears. If you increase the number of the features, or if you increase the complexity of the model H, your bears will decrease, keep decreasing. Okay, and the variance is orange. But your variance will start to increase because if you're at some data at some time point, the summation of these two will be minimum. So that's where we trying to obtain our model. We trying to build a model such that the sum of the bears and the worms is minimized. Minimum risk is minimized. So total error will equals to the bears square plus the worms. Okay. So as the degree freedoms, so the x-axis here is the degrees of the freedoms. Of splines. Degree freedoms of splines. So, which means if we have 2 degree freedoms, we have the very simple model. Like linear regression, if we increase the basis functions in spline, we have the very complex nonlinear model H. Okay. Okay, so that's all I want to cover today. Yes, thank you.